Hi everybody, thanks for joining me and Sandeep today to walk you through a real life scenario of minimizing the job loss while maximizing the spot utilization for your workloads running on your cloud data lakes. Today we are going to walk you through a series of steps which one of our customers who is industry leading content management cloud platform took to minimize these job losses while keeping the cost check by maximizing the spot utilization. It's basically an approach where what you're looking at is that you will get the maximum benefits with respect to the models you're running, but while you're always worried like will it shoot up the cost if you do too much of iterations or too much of ETLs you run. So bringing best of the both worlds, these are the following steps they took. Before we go into the steps they take, let's walk you through their workflow scenario. So here what you see is this is the daily workflow they have to run a predictive models for their clients who are using their content management platform. On the left hand side, as you see, there is large amount of data which they are getting from their product, line items, purchase orders and everything, and they're seeing how people are utilizing the platform with respect to the content management. Now they take this data and what they do is they perform a daily data abstract, transform it and load a ETL job. It is run on the Apache Spark. When the output comes, it's used to run like sophisticated ML predictive models on daily basis. So it's pretty much, you can say, not real time right away, but if you look at the way people are using and every day they need a customized response or tailoring to the needs of whoever is the user or the account, they're pretty much running close to it. So the workflow looks simple, but when you're looking at it from the perspective of a lot of customers, a lot of users, etc., running from multiple angles, and you are trying to feed all of them, there is a challenge with respect to the complexity and the scale which comes with the concurrent users coming in here. So let's go through their operation challenges which made them take the actions. So as you go through this operation challenges, we have the amount of data, and as they are running this ETL, what they are seeing is there are three type of issues they are running into. And the issues they are running into is while doing the daily data abstract, transform, and the loading the ETL job, is like the jobs fail intermittently, right? There are some which execute, some fail, some don't even start, so they have those issues. Then they have reliability issues with respect to, okay, even if they have resolved this intermittent issue, will it run end to end completely? Like, will the loss of the compute node or the spot, will it basically cause issue for them again? So they are running into all these type of scenarios. And then lastly, which used to bug them quite a bit, was the non-visibility with respect to troubleshooting. So one thing is you run the job intermittently, it works out, you have reliability issues, you're working with a black box and you're not able to see in like, okay, what is happening, why it is failing, what can I do with respect to fixing all this problem. So rather than having an automated workflow with respect to having the ETL job run successfully, this used to take approximately more than 46 minutes per job. So what it was causing is an issue is with respect to, first and foremost, is a bad client experience. So the models were not able to basically come to the closure at the time they were supposed to, and then roll it out as a customized offerings for whatever recommendations they were building. So they were having a bad client experience, and to solve the problem they were trying to get all type of compute resources so that there is minimizing the job loss, but it was increasing their cost. So they were running into both the issues here, like cost pressures and also the customer experience pressure. So what they did was, interestingly, these are the three steps they took. They addressed the challenges step by step. So first act they went was they started to use heterogeneous cluster configurations. So they got multiple type of heterogeneous nodes and then maximize the Spot node availability with it. After maximizing the amount of Spot which can be available to you from different configs so that the Spot loss is minimized, what they did was, rather than having everything out there and then having artificial bill go up, they ensured the reliability in the Act 2 with the intelligent Spot management provided by Qubole Data Lake platform. So after Act 3, as we have seen, the first one solved their problem of intermittent failures. The second one solved their problem with respect to when you look at reliability issues. The third one, which I talked about, the troubleshooting, they started to go back and then visualize and optimize jobs with SparkLens on Apache Spark. To walk you through exactly what they did, what are the results they saw before and after, I will hand it over to Sandeep, who will walk you through this scenario. Sandeep, over to you.
Thanks, Dhiraj. Now that we've looked at different operational challenges that the customer was going through, let's take a look at different actions that we took and the impact that those actions had on customer's cluster as well as customer's Spark application. Action 1 was to maximize Spot utilization with Qubole heterogeneous clusters. Action 2 was to ensure reliability using Qubole's intelligent Spot management. And action 3 was to optimize the customer's Spark application or Spark job for performance using Qubole SparkLens. Let's take a deeper look at each of these actions. Action 1, maximize Spot utilization. Why is it important to maximize Spot utilization? Well, the obvious benefit is the EC2 cost savings. Spot nodes can be acquired for up to 90% discount as compared to on-demand nodes. And that can result in significant EC2 savings for the customer. Let's see how that's done. A typical big data cluster comprises of a master node and multiple worker nodes. And each of these clusters, each of these nodes are configured to use a particular Amazon instance type. So the master node is configured to use an Amazon instance type, which is generally compute optimized or general purpose. And worker nodes are configured to use another worker instance type, which is memory intensive. And additionally, in Qubole clusters, you can define your cluster's auto-scaling boundaries with min worker nodes and maximum worker nodes. And optionally, you can also choose a fallback to on-demand flag, which kicks in cases where that worker instance type is not available in Spot market at the time of request. In those cases, Qubole will fall back to on-demand when this flag is enabled. And that way the workloads SLAs are still met because cluster is running at sufficient capacity. If the flag is not enabled though, Qubole will keep on retrying to get that Spot node, and that can add further delays in job processing. So both of these options are not very ideal, and that's where Qubole's heterogeneous clusters comes into play. So with heterogeneous clusters, apart from configuring clusters auto-scaling boundaries and master and worker instance type, you can also additionally configure a bunch of secondary worker instance types. And in the same scenario where that primary worker instance type is not available in Spot market due to low availability or high demand, these secondary instance types could be used to fulfill that request, and that maximizes chances of getting Spot nodes. So there is obviously a caveat with Spot nodes. They come at 90% discount. So what's that caveat? The Spot loss risk. So a Spot node can be taken away by AWS with a short 2-minute notification, and that could result into job failures, or it could introduce reliability issues in your clusters. Now this takes us to our action 2 that we took to ensure that there is reliability in the clusters with Qubole's intelligent Spot management. Let's take a look at that now. Qubole platform out of the box provides features that are geared towards ensuring reliability in high Spot clusters. The intelligence includes provisioning of important daemons like application master on stable nodes. With that, if a task fails due to Spot loss, application master can retry those tasks on surviving nodes. When AWS provides a spot loss notification, Qubole immediately puts those nodes into graceful decommissioning. With that, Qubole stops scheduling new tasks on such nodes and also restores state from those nodes that are about to be lost onto the surviving nodes. Tainted task management is another feature that dynamically adds resources to the task when required and mitigates executor out of memory kind of issues. So there is a lot of resilience built in Qubole platform, most of which comes out of the box. Apart from these out of the box features, there are a few best practices that the cluster admins need to follow in order to maximize spot utilization while mitigating spot loss risk. Let's take a look at those recommendations. First and foremost, Qubole heterogeneous config needs to be used. With heterogeneous config, at least 5 secondary instance types need to be configured. When a spot loss event occurs in AWS Spot Market, it typically impacts the entire instance family. So diversifying across different instance families will help mitigate that risk. Configuring the cluster with multiple subnets, ideally one subnet per availability zone, will help, and it kind of enables a powerful feature in Qubole called intelligent AZ selection. At the time of provisioning the cluster, Qubole locks down on a single availability zone, which is either cost optimized or capacity optimized based on customer's preference. To avoid spot loss risks, capacity optimized strategy is recommended. And spot loss aware provisioning is another feature that avoids bidding for Amazon instance types that are experiencing an active spot loss event at the time of request. Lastly, we've observed that spot loss risk is directly proportional to the amount of time it takes to acquire a spot node. So with that data point, using a lower spot request timeout is recommended. Now let's take a look at this. Look at the impact that these recommendations had on our customers' cluster. First two data columns represent immediate impact, and last two data columns show the impact over a longer period of time. As you can see, the spot utilization improved significantly from 56% before the job was optimized, or the cluster was optimized, to 88%, and spot loss rate was 34% before the optimization, and it went down to 0 after optimization. Last two columns show the aggregate view of over a longer period. So before the optimization, over 72 cluster instance runs, spot utilization was only 66%. But after optimizations, over 290 cluster instance runs, that spot utilization went up to about 80%. Additionally, spot loss rate in before scenario was about 9%. Versus it came in an after scenario, it came down to 1.5%. So this overall increased the spot utilization by 20% and dropped the spot loss rate by 83%. Now that completes action 1 and action 2 and their impact. Now let's take a look at action 3, which was geared towards optimizing customers' Spark application. Qubole developed and open sourced a Spark application profiling tool called SparkLens. Every Spark job that gets submitted through Qubole Analyze interface comes with SparkLens metrics out of the box. Let's take a look at these metrics and also see how we use these metrics to optimize customer Spark application. So Qubole SparkLens emits application level metrics and stage level metrics. So let's look at application level metrics first. Every Spark job runs either in driver phase or executors phase. Executors phase is where most of the parallelism happens. So the idea is to reduce driver side compute to as little as possible and make sure that the job runs in executor phase for as long as possible. Driver wall clock is total time taken by driver to complete the execution. Executor's wall clock is an aggregate time taken by all the executors to complete their execution. Total wall clock is driver wall clock plus executor's wall clock. Critical path is the minimum possible time for the application assuming unlimited resources. And ideal application is minimum possible time for the application assuming perfect parallelism with no data skews. In addition to application metrics, Qubole SparkLens also emits per stage metrics. Wall clock stage percentage is time taken by current stage over total time taken across all the stages. So this data point can be used to identify a stage that is turning out to be a bottleneck for your application and optimize that stage and reduce or improve the performance of your application. P ratio defines the degree of parallelism of that stage. It's basically a ratio of number of tasks over number of cores. So a P ratio which is less than 1 means that you have too little tasks and too many cores, which will result in resource wastage, too many cores sitting idle. And P ratio greater than 1 would mean that you have too many tasks but too little cores. That means a lot of tasks are waiting for cores to be available. So none of these two are ideal scenarios. So the idea is to have P core ratio or P ratio to as close to 1 as possible. Task queue defines degree of skew. So it's basically a ratio of largest task duration over median task duration. Task stage queue is the ratio of largest task duration over task stage duration, total stage duration. And OI ratio is total output of the stage over total input. Apart from these metrics, SparkLens also runs a simulation model on your application and gives emits the results of that, giving the scenario like what the impact would be if you added more executors, and what would be the impact of that on total cluster resources or application resources and on time as well. So now let's look at the actual Spark job that we optimized over a few iterations. So first, what I did was just enabled SparkLens for that customer's application and ran that job. The job completed in about 46 minutes. One thing that I immediately spotted was there was a huge disparity between total wall clock time and critical path, 46 over 7 minutes. Also, P ratio was extremely high at 333, which meant that there were lots of tasks waiting for cores to be available. And on top of it, a simulation model also confirmed that just adding 100 executors or increasing the executors to 100 would improve the performance of the application. So next action that we took was to increase max executors from 20 to 100. So with that change, in the next iteration, we saw that total wall clock came down significantly from 46 minutes in previous iteration to 16 minutes in this iteration. Additionally, P ratio came down significantly from 333 to 50. And on top of it, simulation model confirmed that if we increase the executors count to 400, estimated duration will come down drastically by about 50% to 7 minutes. So that was the next action that we took to increase max executors from 100 to 400. Now in this iteration, when we where we changed the maximum executors from 100 to 400, we expected the job to complete a lot faster, but that didn't happen. In fact, the job ran a minute slower than the previous iteration, and it had to do with upscaling that added certain delays. So Qubole clusters are designed to save customers EC2 costs. So clusters will come up at minimum configuration, and in an event of upscaling, that's when we'll start adding more nodes to the cluster, and that kind of added some minor delays to the job, and that's why we did not see the total wall clock time increased. So the cue that we took from here was to keep maximum executors to 400, but acquire more nodes in terms of minimum executors, bump it up from 20 to 100. So that way we acquired more nodes upfront for this job as this job demanded that. So in next iteration, we increased the minimum number of executors from 20 to 100, and there we saw a significant drop in total wall clock time from 16 or 17 minutes in the previous iteration to 9 minutes in this iteration. We also saw that P ratio remained flat at 17 compared to 15 in last iteration. And lastly, the model estimation confirmed that adding more resources or more executors would not help in this beyond this point. So this was the sweet spot that we identified for this Spark application. So here is the impact summary of all three actions on customers cluster and Spark application. Spot utilization increased by 20%, spot loss rate dropped by 83%, and total wall clock time reduced by 80%. That's it from me and Dhiraj. Thanks for listening. Bye.